Okay, so to begin, before we start talking about the 4 types of symmetry in terms of nature, we're going to just give a brief description of what is symmetry so that we kind of have an idea of what we're talking about and a little bit of a baseline amount of knowledge. So when we're talking about what is symmetry, we're talking about an object itself going through a rigid motion that moves the object back onto itself. So another way of looking at this is saying that symmetry is the property of an object that looks the same to an observer at different vantage points, but instead of talking about the observer moving around the object, we're talking about having a observer that stays still and the object moving around without changing any of the dimensions of the object. So we're talking about moving an object with an observer standing at one vantage point as opposed to having a object that stays still and the observer that moves around it. So that's kind of our baseline knowledge, and then I'll go into more about what a rigid motion is. Okay, so I previously explained a little bit about symmetry and the definition of symmetry so that we can have a baseline of knowledge for going over the specific types, and I mentioned something called rigid motion. So I'm just going to give a little bit of a descriptor on what rigid motion is in the terms of symmetry. So as said on the slides here, a rigid motion is a motion that does not change the distances or angles of a figure. So it's the act of taking an object and moving it from a starting position to an end position without altering its shape or size. So this would mean if you stretch it, tear it, bend it, or any other word for change it or move it, then this is not a rigid motion. So the distance between any 2 points on the figure, say X and Y, in the starting position must be the same as they are in the end position. So a difference between a rigid motion and not a rigid motion would simply be a rigid motion does not change the shape of the figure, and a non-rigid motion is where the figure is altered. Okay, so now we're going to talk a little bit about rotational symmetry and a few examples of how we apply that in nature. So baseline amount of knowledge for rotational symmetry at this stage is it's when an object is rotated on its own axis and the shape of the object remains the same. So we have to have a fixed point for rotational symmetry to happen, and the fixed point of a rotationally symmetrical movement is called the rotocenter, and it is the only fixed point that we're going to have in the rotation, and this will be true for all rotations. Okay, so the rotocenter must be in the center of the object. So if we're looking at our slides here, we have kind of that hourglass shape, the recycling shape, and the star shape. So for the hourglass, it's going to be right where the two curved lines meet, right in the middle. It'll be right in the direct center of the recycling sign and right in the direct center of the star, and that are mapped out in the blue dots there. So those are our rotocenters for those points. So a rotation is a proper rigid motion like we talked about before, and that's where the left and right clockwise and counterclockwise motions are preserved. So we are not altering the shape of the object in any way, shape, or form. Okay, so now we're going to look at kind of the nature examples. So I have 3 here. I have 2 flowers and a starfish or baby starfish. So remembering that a shape with rotational symmetry looks the same even if you turn the shape around. So another way to think of it is to look at these following examples and see that if we pick a center point of these examples, which are the same as our black and white photos, we'll have the center of the 2 flowers and the center of the starfish, that they are going to be able to rotate on that rotocenter and maintain rotational symmetry. So no matter which way you spin the spiderwort from the axis point, which is O, it'll remain and look the same and have the same dimension. So those are examples of where we see it in nature. Okay, so the next thing that I'm going to talk about is the second type of symmetry, and that is reflectional symmetry, and I'll be giving some examples again of how it is in nature. So the baseline knowledge that you need for reflectional symmetry is that it is a mirror image that you have both sides of the image that are exactly the same on one axis or one line. So it looks like when a central mirror line can be drawn on it, providing that both halves of the picture are symmetrical to each other. So we have a lot of examples of this in nature, which I will go over in a second. I just want to go over a couple technical things about reflections more than just saying it's a mirror image. So a reflection is completely determined by its axis L, which is the line that goes through the image. So you can see that in the examples. You can see it in the water and the butterfly and the snowflake, that there is a line that goes through it and it's a mirror image on either side. A reflection has infinitely many fixed points because each point on each side is fixed because it doesn't move. And we're going to talk about rigid motions again, because a rigid motion in this case, it doesn't move. And when a rigid motion that doesn't move the object happens, it's called an identity motion. So it might be silly to call it an identity motion a motion because it doesn't move, but there are reasons to do so, and this is how we classify symmetry in a way. So we didn't move the object, but it is still a rigid motion because it is an improper rigid motion. So it's a rigid motion without movement because we're just getting a reflection, and that creates an identity motion. So we have this example here in water, butterfly, snowflake. You can see that there is a fixed line, a fixed axis with an identical mirror image picture in both cases. I'm using perfect examples here. Obviously, in nature, you will get imperfect things. Like you may have a butterfly that has an injured wing on one side, so it's not an identical mirror image picture. But in this case, we're saying that in perfect scenarios, there are so many examples of reflectional symmetry in nature.
Okay, so thank you so much to Blythe for going over the symmetry, rotational, and reflection types of symmetry. And now we're going to move on to the third type of symmetry that we can see in nature, which is, drumroll, translation symmetry. Okay, so we can define this as when one shape is repeated into an object to make a pattern. So translation symmetry does have a vector of translation, which would be like an arrow showing the direction and the length. It has no rotation or reflection in this, and the angles do not change the size or shape, but the location can change by going up, down, left, and right. And a really good example that we've provided here on the slide would be an example of the honeycomb. So we can see that in nature, and we can see the consistent pattern as well as it does go up, down, left, and right. It goes in all the different directions. Another example we can see of translation symmetry would be snakeskin, actually. Okay, so now we're going to move on to glide reflection, and we have a quote from the textbook here, and I'll just read it out. It says, "A glide reflection is a rigid motion obtained by combining a translation, which is the glide, with a reflection. Moreover, the axis of reflection must be parallel to the direction of translation." So I also included that every glide reflection has a mirror line and translation distance. So in the picture, we can see the translation parallel, which is the foot being repeated, the repeated object in order to be the pattern. So just in this picture here, we can see the glide and then reflect, glide and reflect, and it would just continue throughout the whole process. So the example in nature that we found, which is very similar to the picture shown, would be animal prints in the snow. And the really cool thing about this project is that it is winter time, so whether we're walking around on campus or walking around to do errands, we can see our own footprints, we see other people's footprints, as well as we see animal footprints. And then now it's just stuck in my head of glide reflection symmetry. Okay, so just to conclude our presentation, we just wanted to clarify what we went over and what we learned today. So we went over the 4 different types of symmetry. We have rotational symmetry, reflection symmetry, translation symmetry, as well as glide reflection symmetry. And then I just provided a little picture here, which would be more seen like in the class textbook, but honestly, it was a really good start for me to really grasp the concepts of what we are learning. And just for like fun, or if you have the time, we really encourage you to take a walk around and see where you can find nature and symmetry. So as talked about in the glide reflection, we have the footprints here, and honestly it's just like really cool to see this and be able to relate it to math in a way I never thought I could. So thank you guys so much for listening. We really appreciate it, and we really hope that you got the concepts that we're trying to come along with. And then quickly, my references from the class textbook as well as our pictures.